Okay, good morning, everybody, and thanks for coming. It's always great to have an event like this coming for the Ph.D. defense of Viranger Pereira. My name is Semken. I'm a professor in School of Earth and Space Exploration, one of Viranger's co-advisors, and also want to mention his other co-advisor, Professor Erik Asphaug, who for medical reasons was not able to be here today, and Professor Enrique Pavoni has graciously agreed to step in for him to be the official co-advisor for today. I also want to recognize the other committee members for Viranger, Professor Lindy Elkins-Tanton, Professor Ariel Anbar, and Professor Mark Robinson. Well, I will say a little bit about Viranger. Viranger got his Bachelor of Science degree in Physics and Aerospace Engineering at Cal Poly Pomona, and his Master of Science in Planetary Science at UC Santa Cruz. He's also been a teacher and a mentor, and if you look at his CV, it's full of recognition and awards. A little something about Viranger. You know, I'm a science education researcher, and Viranger originally came to ASU with the interest of doing planetary science research, and one day he knocked on my office door and came in and told me that he was interested in pursuing some research in science education. Had no background in that before, and that happens. Students get interested in that field owing to their exposure to teaching, good teaching. But it can be a pretty tough road to hoe if you don't have no experience to get up to speed on the research and the methods in order to make a valid contribution in the field. And I didn't mince any words with Viranger. I said, if you want to do something like this, you're going to really have to put some extra effort into it. And quite honestly, I've seen a lot of students who tried that and they've never really followed up on it. That was the first and last time that I ever underestimated Viranger Pereira. Okay. Suffice it to say that he did all of that and more. Okay. We already have a paper in press in one of the more prestigious and high-impact science education journals related to his work, which he did by coming on with the Center for Education Through Exploration. Pretty much everything that I've seen him do is exemplary. His science, his research. He has a very, very serious and motivated attitude toward his work, and I'm really, really proud of what he's done. And I'm really looking forward to a presentation with probably the most unusual title I've ever seen for a PhD. So I've probably said enough here. I just want to say welcome to everybody, and I'll turn the floor over to Viranger, who's going to present on Driven by Affect to Explore Asteroids and the Moon. Viranger.
Thank you, Steve. Thank you for the nice introduction. As Steve mentioned, I'm going to talk about three things today. I'm going to talk about asteroids, I'm going to talk about the moon, and then I'm going to talk about science education. And I know what you're thinking, like Steve alluded to, you're looking for a word. That's the word you're looking for. What does this have to do with anything, right? So I want to propose this word, this odd word that was in the title, affect, and it's from psychology. It means this domain of attitudes, emotions, and interests, and values, and how that drives what you do as a person. So let's start with asteroids. I'll get to affect in a bit. I'm going to quickly talk about this fun little project on asteroids. So what are asteroids? They're kind of the leftover material from the planet formation process. And Erik, who is really good with words, he had a nice way of putting this. It's like the stuff that's on the floor of a bakery, right? The leftover material after the bread has been made, and planets are the bread. So it's a nice way of putting what asteroids are. So this is what they look like. They have odd shapes to them. That's a potato. They look like potatoes, you can admit it. But the question I want to ask is, what's inside asteroids? What are they made out of? So we don't have a lot of seismic information, so we have lots of pictures, and so we can maybe say something about it from that. So the first idea of what the insides of asteroids might look like, comes from their spin. So there's a lot of information here, but the important point is that spin of asteroids plotted along the y-axis. As you go up, things get faster. And all the dots are individual asteroids by their sizes. And what you'll notice up here is there's an area that's missing. There are spins for given sizes that don't seem to exist. And the idea is, well, if you spin asteroids up, maybe they just rip themselves apart. Right? So that's why there's a spin limit. It kind of gives an idea of, well, maybe that's what, it helps us understand what the insides of asteroids looks like. So the other point is their void space, how much empty space they have. So again, there's a lot of information, but the point is to look at the porosity. It's a comparison between the bulk density of the object and the density of material that it's made out of, right? So if there's less, it's a less dense object than, say, the density of rock, then there's empty space, and you can see a bunch of asteroids plotted where there's a lot of empty space inside them. So we put these two ideas together, and there's this idea of that most asteroids are probably rubble pile objects. They're objects held together by gravity and possibly cohesion. So you put those ideas together, and you get this notion that asteroids are rubble piles. So when you shake rubble piles, something interesting happens. And there's this effect called the Brazil nut effect. And basically what happens is if you take a mixed can of nuts or a bowl of nuts and you shake it, over time the larger Brazil nuts will rise to the top. And you can do this with cereal as well. You might as well call it this Cheerios effect. You can take a bag of cereal, shake it, and then the cereal will come to the top and the dust will go to the bottom. And this is what happens to granular material of different sizes and comparable densities. So people have argued that this happens on asteroids, like Itokawa. Like this boulder here, you can see these big boulders are argued to be from this effect of asteroids being impacted, shaken, and then all the larger objects come to the surface. And on the right-hand side, it's plotting gravitational potential, but it's the idea is if you take something at this level and you raise it up, it has more gravitational potential energy. So the red, the higher numbers are higher areas. And if you look, you can see there are large boulders in where the red colors are, even right there. So the argument is that larger objects have come to the top, quote-unquote top, of asteroids. And some previous work has looked at this in cylindrical configurations. You put a big ball amongst other smaller marbles, you shake it, and then you can see this effect happening. You can see the larger object popping up to the surface. And so when you put these together, arguing that, okay, this effect, where you have a large object rising to the surface as you shake it, happens on an asteroid. But the point is, this does not look like this. This is a cylinder with a bunch of marbles, and this is an object that's three-dimensional, held together by gravity. So what I was thinking a couple of years ago was, why don't you just make a rubble pile? You can do that with computer simulation. This is done by PKD-Grav, which is a code that's been developed over several years. So you can make a rubble pile. Right? So now this looks more like an asteroid. It's still spherical. It's not ideal. But it's a lot better than doing it in a cylinder, because now you have an object you can shake. Now this object has properties roughly the size and mass and things like that of an asteroid, has low density, and the point is it's made out of two different size objects. Larger objects are 80 meters in radius, and the smaller objects are 40 meters in radius. So this is a larger object, even though it looks like a bunch of marbles. So for comparison, we could take Sun Devil Stadium and look at the size of the smallest object, which is big. So they're very large marbles, but they represent asteroids.
That's about what happened on Saturday.
They weren't using the field, so I used it on Saturday. So now what we can do is take this aggregate and start shaking it to mimic impacts onto asteroids. And on the right side is a histogram showing the locations of the larger red particles and the smaller yellow particles. And what you saw was it started almost the same, and over time that histogram spreads. What you should be seeing is the yellow particles are sinking into the interior while the larger red particles are on top, and as you watch over and over. So what I'm doing is giving these particles random velocity, letting it settle, doing it again and again and again 500 times for 100 days. So, and the maximum velocity I'm giving it is about 50% of its escape velocity. So it's being shaken quite vigorously, not up to the point to rip it itself apart. Right? So you want to shake it vigorously just to illustrate the point but not so that it comes apart. And you can see now where it started off with the same shape for the histogram, now it's spread out, where it's showing that the yellow smaller particles are inside the object and the larger red objects are clearly outside. And just for comparison, that's what it started like, and now we can see this Brazil net effect happening on a three-dimensional object. Now we want to compare it just for kicks to see if it happens without friction, and it does. You can turn off friction and you don't really need it, and the effect still happens. One thing I want to point out with this figure is, again, I'm showing histograms for three different states: the initial 0 days, the middle, and then the final stage. The top is the external view, the middle is a cut through, take the aggregate and slice it through the middle, and the bottom is, again, the histograms. Notice one thing, that this area, that very inside of the asteroid, doesn't change over time, right? So you see particle segregation or sorting in the outer layers, but not in the interior of the object. So this might imply that actual asteroids might also have sorted outer layers, but the inside stays sorted. So I like to do my summary, but I'd like some help from you to do it. Asteroids are laundry piles. Potato piles. Come on, you know this. Rubble piles, very good. What effect happens on asteroids, most likely? Peru. Brazil nut. And like I said, which layers are getting sorted? Outer layers, right? So, like Steve said, this is a paper out in Icarus. There's a lot more detail I can't get to right now. So you can please check out the paper. So the next topic I want to talk about is the moon. 1 second. And specifically, I want to talk about the thermal evolution of the moon. And before I get to that, I'm going to show you a little clip of the Apollo astronauts. Let's see.
White craft. And it's about, oh man, look at that. Look at it. Almost 320 in there. Guess what we just found? Guess what we just found? I think we found what we came for. Crystal rock now. Yes, sir. You better believe it. Yes, there are flash in there. Oh, it's all flash. Check it. As a matter of fact, oh boy, I think we might have ourselves something close to the Horodyskyj. Because it's crystal in there, just a bunch of just almost all flash.
So they're pretty excited. They found this rock. It's called the Genesis rock. And like he said, it's mostly made out of yeah, 99.99% of it is made out of plagioclase. And that was one hint that the moon, after it formed, was in a molten state. It was mostly molten. It was one of the hints for that. The other hint is how the moon itself formed. This is the canonical moon formation scenario, where you have the proto-Earth and a Mars-sized object slamming into each other, produces a lot of debris, and out of that debris comes the moon. And what I want to point out on the right side is the temperature of this debris material is in the 1,000s, 2,000, 3,000, 4,000 Kelvin range, so it's in a molten state. And you can expect when the moon forms, after this rather energetic event, it would be in a molten state. So from these 2 points came this idea of a lunar magma ocean that way back in time, after the moon formed, it had this mostly global ocean of magma, about 1,000 kilometers deep. It took about 10 million years to cool, and that's what we're seeing today. We see a moon that has a North Acidic crust, and that piece of that crust is what they were excited to find. Genesis rock is argued to be a piece of this original crust of the moon. And in between, going from this molten state to the final state that the moon is today, it goes through this transition where it cools over time, and initially all the solidified material falls to the interior, and this solid interior grows to the point where most of the magma ocean has cooled, about 80%. And at that point, this interesting mineral, plagioclase, becomes stable, and it's, weirdly enough, less dense than the magma it's in, so it floats to the top and forms this conductive lid on the moon, which slows down the cooling process and continues. So this it's adding material to the interior as well as adding material to the lid. So it cools and cools and eventually becomes the moon that we see today. So that was a cartoon that was oversimplified, and then here with this cartoon I tried to put everything that you have to consider when you try to think about cooling a lunar magma ocean. So there's a lot of stuff, and for one thing, which Lindy has done, is so you have to consider the crystallization process of which minerals are stable at what point and what depth. You have to be careful about that. You have to do that, do those details. But for this work, I'm going to focus mostly on impacts and how that process affected the cooling of the moon. So let's go back to the moon formation scenario. And you saw this before, where the proto-Earth is being slammed into by a Mars-sized object. And there's a lot of debris that's generated, as you can see. And I said that that debris is what becomes the moon. But there's some debris that escapes the Earth-Moon system and goes into orbit around the Sun, about a mass of the moon worth of material. That's a lot of material. And so Alan Jackson, who's back there, he worked on looking at this debris and how it evolves over time.
Isn't that the best title ever?
Oh, yes. Yeah. This is Alan Jackson's proposal, which he got a NASA proposal for doing this work, and he called it Stop Hitting Yourself, which is what the Earth and the Moon are doing. So I've drawn in blue orbit of the Earth at 1 AUs, the yellow is the Sun, and it'll start right there. You'll see the Moon forming impact, generates a lot of debris, and then you'll see the evolution of this debris over time. So you can see a lot of material that's floating around the solar system, and what's interesting is these orbits will come back and start hitting the Moon and the Earth, so thus stop hitting yourself. So there's a lot of material. How much material? Let's look at one more thing. The mass coming from this. So I'm plotting the Moon and the Earth, so we'll look at the Moon first. The blue line is the amount of material coming and hitting the Moon over time, and you can see it goes on for about 100 million years. And the blue line assumes that the largest debris object was 500 kilometers in size. The orange is if you assume the largest debris was 100 kilometers in size. Smaller objects tend to grind itself out and kind of break itself apart. So that's why the larger object you see a more sustained bombardment. Now the red is the Earth. The Earth is bigger, so it gets a lot more material. And the same thing, you can see the amount of material hitting the Earth over time. Again, dividing up, if you make the largest item the smallest, largest object of the debris, 100 or 500 kilometers. So for reference, those who study the Moon know the late heavy bombardment is argued to be one of the more cataclysmic or high bombardment rates on the Moon, and that's down here. So there's a lot more material than is assumed for the late heavy bombardment. So a lot of material is coming in. And so going from left to right, what I'm doing is plotting the Moon at 10 Earth radii, and then the Moon at 60 Earth radii away. So currently it's at 60 Earth radii for reference. And so we're going to use this 10 Earth radii number, because that's pretty good for the early Moon. And as you can see, it doesn't really change much. I mean, you can barely see the difference. If you really want to know what the difference is, you can look at this point and compare. There's a bit of a drop-off. But other than that, you can't really tell. So this material is coming in. What's going to happen is, remember that conductive lid, all this material can make holes into this lid. This lid slowed everything down. It made the problem a conductive issue. Now when you break the crust, now it can release a lot more energy and cool faster. The problem is this whole production process is dependent on a lot of things: the size of the impactor, the velocity, what the crust is, and the thickness of the crust, a lot of things. And so Alan's leading an effort where he's running hydrocode simulations to understand this process, but that's ongoing work. So for now, what I'm going to do is basically use a simple conversion, take the mass and convert it into an area of holes, right? So we know how much material is coming in, and we can assume by assuming a certain K, we can get a certain area of holes. And by varying K, you can vary the bombardment, right? So a large K means fewer holes. So going back, so this is where the starting point is. We start with a magma ocean about 1,000 kilometers in depth. and this is where the thermal model begins. But I want to question what happens on the surface. What does the surface look like? Is there magma everywhere? Like if you went back 4 billion years and saw the moon, would you see this giant ocean of magma? And we argue no, because there should be some amount of quenched crust on the top. And quenched crust is just the magma that's quickly cooled and solidified, and that tends to be more dense than the magma itself. So it should sink. If it forms, it should sink. But previous work argued for Io that it should sink after a point, where initially, because it will trap volatile material, that material should be able to be less dense than the magma itself and stay afloat on the magma ocean. Now, if it gets too thick, then because of the density of the material, it should sink. But in between those points where it should be equilibrium condition, where there's some thickness of quench that is in equilibrium with the convective flux that's coming through the bottom and the conductive flux that's going through the quenched crust and the radiative flux that goes through the surface. So the balance of those three things should give us a thickness of quenched crust, and that should evolve over time. So we put a quenched crust on the top of that magma ocean right there, and the steps of this process is take the initial state, take the magma ocean, take a small volume of that magma ocean and solidify it, and release the heat through the surface, and do it over and over again until you basically have gotten rid of the magma ocean completely. And this is something that Lindy's done before. So when it comes to the heat that's being released, it's the heat because of the solidification of the magma ocean itself. The cooling, the temperature of the magma ocean, it's reducing its temperature, the solidification of the quenched crust, and also other things like radiogenic heating or tidal heating. All these things are what I consider heat, the things that you have to release through the surface and do it over and over again and cool this magma ocean. And also, like I talked about before, you have to consider impacts. As impacts come, they'll produce holes, and obviously the energy released through a surface here and the surface there are different, right, because of the hole that's been produced. Now, that's the step. The first step is that. Now, after a while, because the magma that solidifies is more dense, it'll go to the interior. The solid interior will grow up to the point where there's about 100 kilometers worth of magma ocean left. At that point, plagioclase, that mineral, becomes stable. It starts making an orthositic crust, which floats to the top of the moon, forms this primordial crust of the moon. But again, impacts still happen because it happens over 100 million years. So you have to keep track of these holes that are produced and account for the energy released that way. So let's look at some results. What I'm doing here is plotting the remaining lunar magma ocean, starting with 100%. It'll go to 0. And what I want to do is try to reproduce what Lindy did into 2011 and see if I can get basically what she got. So she got 10 million years to cool, and you can see that it starts with 100%, rapidly drops off, because in her work she didn't have a quenched crust. It's radiating away as a free surface. It rapidly cools, and then this part, it's slow because now you have that conductive growth there, right? So it takes about 10 million years. If you really pay attention, it's not really 10, it's like 26. But there are some differences between the two models. One thing, I don't do geochemistry in this. There's only the physics. We have quenched crust, and we handle the surface temperature slightly differently. So there's some differences, but roughly you can see it's in the same ballpark. So that's the blue line is reproduction, or trying to reproduce basically what she had. And then the dotted orange is when we take her model and add quenched crust to it. You can see it doesn't change the cooling time of the magma ocean. What it does is it just shifts the early phase a bit later. So the moon stays 100% or mostly molten for longer. But notice it's in log, right? So it just shifts everything a little bit, but it doesn't change the overall cooling time by adding quenched crust. Now I want to give a feeling of what the K does. As I mentioned before, K is a conversion between the mass of the impacts coming in and the area of holes being produced. And you can see that K, when it's very large, the amount of holes that the surface of the moon has at the very end, after everything is cooled, is 0, right? Basically 0. So if you can dial up K incredibly high to the point where mass is coming in, but it produces no holes, right? So the opposite is making K very small. In that sense, mass is coming in and produces a lot of holes, to the point where after the moon has completely cooled, now the entire surface should be peppered with remnants of holes, right? And you can see how for certain values of K, the entire surface is peppered with holes. And again, I'm doing the comparison between assuming the largest object size for the debris. And like I mentioned before, when the object size is 500 kilometers, much larger, then the bombardment is more sustained, it goes on for longer, and thus it for the same K value, produces more holes. But we use 100 kilometers as a nominal value, because 500 seems a bit high, but I just want to show you the comparison there. So now this is showing the crustal thickness of the moon over time. And what you notice is that it'll get to 45 kilometers, which is roughly the average crustal thickness of the moon today, from 0. So this is the north acidic crust being produced over time. And you can see it starts off about 10,000 years because of that delay. It takes most of the magma ocean has to cool before this crust forms. So it starts forming about 10,000 years, and now it'll get to 45. And we can start with the no impacts case. It should take roughly 32 million years. And then when K is very large, it's almost exactly the same, right? You can see in dashes. When K is very large, it's almost like if there are no impacts. But if you bring K down to 10 to the 5, you can see what happens is that 32 million years become shorter and shorter and shorter. Because you're poking holes at the moon, it's able to release a lot more energy because of the holes that are there. Now you might ask, okay, that's nice, you're poking holes, but a lot of the material coming in, they have kinetic energy. Where does that go? So it's a good question. So I'll show you the same thing, the solidification time of the magma ocean as a function of this kinetic energy. So let's start with no kinetic energy. That's what you saw before. The material's coming in, producing holes, but the kinetic energy just disappears. That doesn't do anything. And what you see is when K is very high, it gets to that 32 million year number. As you dial K down, you can get to 5. Right? So it's somewhere between 32, or roughly 30, and 5. When you don't consider the kinetic energy of the impactors. Now, the exact opposite is all of the kinetic energy of the impactors goes into thermally heating up or adding thermal energy to the magma ocean. That's the one in orange. And you can see that same thing as a function of K. So for every given K, when you add so much energy, then the time it takes for the magma ocean to cool is longer. Right? So in the case where there are basically no impacts, if you add the kinetic energy, instead of 30-something million years, it will take roughly 50 because of the extra energy of the impactors. Now, if you make lots of holes, it becomes the point where it doesn't matter how much kinetic energy you have, the magma ocean will always cool faster than if there were no impacts. So this gives you bounds, gives you adding all the kinetic energy there and adding no kinetic energy there. So the lambda is like an efficiency of converting kinetic energy to thermal energy, and it kind of gives you bounds as a function of that K. So the answer to how long did the moon take to cool could be 5 or 50. Right? And you can ask, who cares? Right?
I care.
She cares. I don't know if everybody else cares. So the who cares comes from a figure from one of Lindy's papers, is if you plot out the ages of the lunar crust, there are lots of ages here, and if you look at the scale here, it spans for 200 million years. So the youngest crust and the oldest crust, the difference is 200 million years. Now notice, this crust is supposed to form out of this magma ocean. All right? So there's a bit of a problem. So Lindy found 10 million years right there, 10 million years to cool the magma ocean. In this work, it's 30, and depending on the impact scenario, it could be 5 or 50. It's still not 200, right? So there's something else going on, And what other people have done is take thermal models and add tidal heating to prolong the cooling of the moon and make it last for 200 million years. Now, if the Lunar Magma Ocean lasts for 200 million years, and the crust has ages that span 200 million years, now it's consistent, right? But then we start poking holes in the moon, right? So this plot is trying to put everything together. It's trying to put holes by impacts, kinetic energy by impacts, additional heating. I keep it general, so it could be tidal heating, it could be something else, but I keep it general. And so let me walk you through it. Again, plotting the solidification time, millions of years. If you take the no impacts case, right, it's about 30 million years without any additional heating. And as you add a bit of heating, you can get it over 200 million years for a bit of additional heating from tidal heating. Now, as you poke holes into the moon, now we're using K 10 to the 7, which is like a moderate amount of hole production. And in the filled marks are when you don't add any kinetic energy, and the open is when you add all the kinetic energy. So again, it gives you a bound, right? So between those could be the actual number, depending on the K. So for this particular K, somewhere in between there, and you can pick your tidal heating value that matches the 200 million years somewhere, and then you have to produce that much tidal heating. And as you get more and more intense in bombardment, you have 10 to the 6 or 10 to the 5, it gets to the point where it's really, really hard to get to 200 million years. Because the highest amount of tidal heating that I could find that anyone's done before is 10 terawatts. Terawatts is 10 to the 12 watts of energy being added, and that's the highest that I have seen someone get up to. So there could be a scenario where the bombardment is so intense that there is no amount of heating that from tidal heating that can get you up to 200 million years. So there's a bit of a discrepancy maybe, but there's a lot still left to be done, but I want to kind of illustrate the point. And I'll come to this summary again. You know the drill, right, by now? So how much mass was released and sent into heliocentric orbits? How much material escaped the Earth-Moon system? About a moon's what? Yeah, right. I think I heard that. So debris would have punctured holes and delivered, kinetic or thermal energy. That'll do. And so the range in order of magnitude, it would have been 5. Yeah, so roughly 1, 2, order of magnitude B. And what's the other one? 100, right? So 100 million years. So it's a big range. This is bad. We know it. There's plenty to be done here. So this paper is in the works. It's almost ready to go. We're just working on this. So this is what it's going to talk about, mostly. How's the time? Still pretty good, right? So you're okay for one more topic? There's a lot, right? But one more topic. We'll do...
We don't want to skip that.
Yeah, so Steve doesn't want to skip that. So we'll talk about education, science education, specifically students' attitudes towards science and how it affects their learning. And when you think about attitudes, such a general term, here's more of an official definition, if you will. It basically is a predisposition to think of something as favorable, unfavorable. When you see it, maybe apple juice right there or coffee, you have some attitude towards them because of a predisposition. So there are 3 domains I'd like to talk about in psychology, and you saw this one, affect, which is about attitudes, emotions, interests, and values. The other one's behavior, pretty self-explanatory, it's just stuff you do. And the other one is cognition, right? So it has certain things that you normally think of in education, because mostly when you think of education, you think of cognition. You don't think of the other 2, mostly. So I want to illustrate the connection between cognition and behavior as an example, and Anna helped out with getting the data for this one slide, so thanks to her. And I want to illustrate the connection between cognition and behavior, and take a moment and think about this statement right here, and think about if you agree with it or disagree with it. So now I'd like to show what the early start students at ASU answered. Strongly disagree, disagree, agree, and strongly agree. You can see most of them agreed with this statement. And why? Who cares? The important thing is it depends on how you answer this question. it breaks you up into two groups. One that thinks that intelligence is fixed, you can't do anything about it, and based on that view, you tend to want to, or appear to, perform well. You seek positive judgments, you avoid assessments, and you stop when you face failure. If you agreed, you would think of intelligence as something that can be changed, and then therefore you try to gain more competence, you seek challenges, and you persist. It's kind of important. And this, by the way, has nothing to do with what intelligence actually is. It's how you think about intelligence is, right? So, and it affects your behavior in such a way, and it's been studied for a long time. So, just like that, I want to see the connection between affect and behavior and cognition in this work. And to do that, we gave out a survey to a bunch of students, and the survey we used is called the Classroom Undergraduate Research Experience, or CURE survey. It has lots of parts to it, but the two main parts I want to focus on have attitudes toward science, 22 items worth of those, and benefits after taking the course. So typical items are such as creativity does not play a role in science, or I can do well in science courses. And in benefits, it's benefits of taking the class. You learn how to interpret results, and to work independently, things like that. These are kind of answered on two different scales. The science attitudes are answered on a strongly disagree or agree scale, and the benefits are answered on a no gain or very large gain scale. Right? So two different scales. And the students we used were from Habitable Worlds, which Ariel and Lev developed over a long period of time. And we took 3 semesters worth of students, 900 or so. We got a few of them, about a half, 450 was our cohort, because of you have to agree to participate in the survey and things like that, and also answer the items themselves. So we chose 451 based on that. And we divided them pretty equally between I-course and O-course. And you may have seen this before. It's something that ASU uses to distinguish traditional in-person degree-seeking undergraduates, and the O-course are fully online students who might not even be in Arizona, right? So again, think about what you think about this statement. You agree or disagree with this statement. And I'm going to show you what the experts of CC thought of this. A couple of years ago, I sent out an email asking you to answer this question. And a bunch of you responded, and some of your answers might be actually in here. And you can see most of you disagree. You think that people should take science classes, which is good. I think those are the libertarians. I don't know. So now we can look at what the students thought of. And on the left are the pre-course answers. On the right are the post-course answers. And you can see lots of changes. Mostly they start with disagreeing with this statement. And there are some changes. As you can see, there are some people who strongly disagreed and went up to strongly agreed, which I think Worlds may have been hate science for some reason. I don't know. So the problem with looking at these plots are really nice, but after a while you start seeing this, and you wonder, you really struggle to make any sense out of them. I think that's the Eiffel Tower, though, but I don't know. So, and the other problem is with these plots is there are 22 of these items. It becomes really, really difficult to make any sense out of them. So the way to do this is to do a factor analysis. You take all these items that students have responded to, and you ask the question, is there something more fundamental that's driving these answers? That you can take the students collectively and ask the question, are there some factors, 1, 2, 3, something small, latent factors or hidden variables that are influencing these item responses? And that's independent to the student. Right? So there's something fundamental to students or humans that may be driving the responses to these answers, and you can get, using nomenclature, the eigenvalues for these factors. So we do this with the science attitude items. There are 22. They broke up into one factor with 8 items, the second factor with 4 items, some that didn't group at all, and one that we excluded because it's not relevant to the class. And benefits items, there are 21, and they grouped into one factor with 11 items, and the rest didn't come into the group. So we have these three factors. The benefits one is easy to name. It's benefits, right? I mean, benefits of taking the class. The science attitudes ones, we spend a lot of time thinking, what do these items, or what are they actually measuring? Because if you read these items, it's not obvious what they are. But eventually, we called it scientific sophistication. We're guessing that those items are measuring a certain scientific sophistication. And the second one is measuring a certain sense of personal value in doing science and taking a science class. So here, what I'm showing are the changes from before and after taking the class. On the y-axis is the personal value item. The x has the scientific sophistication. And it's showing you mean changes of the students, everybody, the I course, the traditional students, and then the O course, the online students. And you can see right away the darkest, the color indicates the number of students in each bin. It's like a two-dimensional histogram. So you can see most of the students don't change, which is probably expected because it's a 7.5-week course. You don't expect fundamental changes in attitudes over a short period of time. So a lot of people don't change. But you can maybe identify, quote-unquote, an ideal region. You want an increase in scientific sophistication. You want an increase in personal value in science, right? So you can identify a region, and some people go there, but it's not very clear. So what I can do is do linear regressions, and here is the post-course SS scientific sophistication factor versus the pre-course scientific sophistication factor, and it's in a z-score, 0 being the mean, 1 being 1 standard deviation away, and 2 and so forth. And what you can see is that if you do a linear regression, the O course students plot higher. There's a bit of higher intercept there than the I course students. You might be skeptical about this, but the thing is there's a lot of data that's plotted in this region on top of each other, so it's harder to see. And in this, the slope and intercept both are statistically significant, but because there are only 4 items in the personal value factor, going from pre to post-course, you can do the same thing, and you see that the O course is higher than the I course, but the slope is not statistically significant. So you can trust the intercept, but not the slopes. Right? So what I wanted to do was really consider grades. How do the attitudes affect grades? And these are the grades that the students got. There is not a lot of difference between I course and O course. Their means and medians are not the same, so you can't really distinguish them. You might notice it's not normal. It makes it slightly of a problem when you try to do linear regression models. You can't really do this with, there's no way to justify that this is normal. It's normally distributed. So what we could do is divide this group up into those who got A's and those who didn't get A's. Make it binary, and in that case you can do something called a logistic regression model. So what it does is it bins people into 2 groups and predicts what's the likelihood of being in one bin or the other. And the bins are get an A or don't get an A. And so that's the probability, 100% chance of getting an A and 0. And based on the ASU GPA, z-score again, so this is the mean, about a B+, that's a B+, I think, right? If you have a B+, you have a slightly more than 50% chance of getting an A grade if you're female. And if you do this for the males, there is an offset. And there's a bit of a gender gap, as you can see. For the same mean ASU GPA, the males are higher likelihood of getting an A. Right? So both of these have been shown before. There is this gender gap and also this strong dependence on your GPA on how you perform in a class. People with higher GPAs should perform better in a class. Now, what I want to look in this work is that attitudes, right? So scientific sophistication and how that affects grades. And what I'm doing here is same thing, logistic regression model for students with a mean ASU GPA, right, of 3.3. If, depending on how they change on this scientific sophistication factor, it changes their probability of getting an A. And again, there's a gender gap again, but the higher you do with this factor, the higher the scientific sophistication is, the more likelihood of you getting an A. So that's I think, very important to show here's attitudes directly affecting grades. And it's not quite behavior or cognition, because we only have a measure of grade to look at, but it's still hinting at the fact that affect is affecting behavior and cognition, which leads to you to getting a grade, a particular grade. So I'll summarize here. Affect includes, with an A, another thing that's with an A, attitudes, right? Which students do better with their attitudes? There's the I course and the O course. Which one's better? Remember, online. Okay, online students are doing better. And along with ASU GPA and gender, what's the other thing that's predicting receiving grades? Sophistication. Yeah, scientific sophistication. Right? There's a factor that is linked to grades. Right? So, like Steve said, this is in press in CD Life Sciences. It should come up next month, I think. So please check out. Again, there's a lot more detail I didn't get to go to. A lot of people thank for this. Lots of people helped. I didn't obviously do this by myself. I want to thank my committee. Erik is not here, unfortunately. Wish him well. Steve, Ariel, Lindy, Mark, and Enrique for subbing in for Erik today. Two people I really like to thank. Alan Jackson, who's back there, who really helped with the asteroid work, the moon work, and Chris Mead for the education work. Without those two, this wouldn't be possible. I'm not kidding. They're actually very vital to this work, and thank you both for doing that. For the asteroid work, mostly these are people who've got me set up with the code. Desireé for introducing the code to me. Derek is the original developer of PKD Graph. Ron and Steve for helping me set it up and run it. Education, Sanlyn Buxner of University of Arizona was very vital in helping us with the education work. David for giving us the information on the survey, and Lev for being actually the person who helped me knock on Steve's door. I actually looked up the email I sent to Lev that he introduced Steve and Ariel to me. My mentor from undergrad, he's been still in contact, which is incredible. Alex Rudolph, and a bunch of teachers. I've had lots of amazing teachers. I want to list some of them here, but really, all of them should deserve thanks. My mom, who's not to be here, but my two sisters are here, so I'd like to thank them, and to my aunt and uncle in Geneva. So, one second. So I like this quote because I think it kind of puts everything together, that affect is important in research as well as in education. You, most of you are researchers, the research that you do are driven by what you find interesting and your values and your attitude to certain things. And that's why I got started on asteroids and the moon. I'm obsessed by the moon. We can talk about that later. But and you can see that there's some link to this as with education as well. So it's something to keep in mind. And not just, cognition is really important, memory and learning the facts, if you will. But there's also an affective component to education and research. So I hope that came across. So I'll take any questions if you have. Thank you.
I'm glad that was being recorded, because I think this is really a great example of a defense that I think other people should see. The usual procedure now is we'll have a little time for people in the audience to ask questions of Viranga, and when we're done with that, we'll dismiss everybody except Viranga's committee, and we'll have a final meeting with him, with the committee members, and they can answer their questions. So, who has questions?
Can you go back to the slide where you first started doing the factor analysis?
Sure.
You mean this one?
No, the next one. Yeah. So presumably you take all this data that you collected from the students, right? And like each of these 22 questions, I guess, were data points in this high-dimensional space, and you did some eigenvalue decomposition and got out these two principal components.
Right.
But then how did you determine what those components were? Did you guys just think about it, or did you go back and collect more data?
So the naming of the factors and what the factors are, yeah, we went back and forth a long time. I think naming these factors was probably one of the bigger things. It's mostly done by looking at the items themselves. So we didn't develop the survey, and it wasn't in some ways done in the traditional way of how surveys are developed. And so we were looking at these eight items, or the 4 items in the other one. to kind of come out to what it means. Now, the other thing is it's not just hand-waving in some sense because, like, especially factor 2, personal value. We think it links to intrinsic motivation. And if that's the case, there's a way of testing that out by looking at, are students behaving that way? People who are intrinsically motivated should be doing things just because. And after they're done with a certain component of the lesson, if there's ability to explore further, they should be doing that. And you can see that in the data. So those who score highly on this second factor should do those things. So it's a way of testing it out. So, and the other thing about the first factor, scientific sophistication, is it kind of is like the nature of science issue. People talk about teaching the nature of science to students. It kind of hints at that. So they both have some legacy to them that we can see, and that's partly how we decided to pick that.
Other questions?
So some of these factors that you found contributed to success in the course, to what degree were those factors themselves correlated?
To each other?
To each other?
I have that. I put this because you're going to do this, right? Because so the blue, the one that is highlighted in blue is statistically significant, but you can see the correlations are really low. And if you're in the physical sciences, you'd laugh at these numbers because this is noise. But in social sciences, when you're dealing with people, they don't tend to line up in linear lines, which is weird. So the correlations are really small. What you see with personal value and scientific sophistication, for instance, they're not correlated with each other. Oh, it's my pleasure. You can see personal value and scientific sophistication is 0.06, so they're not correlated with one another. Sure, they're independent measures of something, which we believe is that. Okay.
In this Brazil nut effect that you were simulating, which I found fascinating, you're getting impacts from objects, but is the spherical object spinning at appropriate rates?
From the impacts?
No, from its natural spin. You put up a plot of how diameter and spin are correlated, so I would assume that this object would have a spin.
Oh, so I started this basically stable, and because of the random velocities that are given, it doesn't naturally have any spin. They kind of cancel each other out. But it's something that we want to look in the future, is give some spin and then do this and see how that affects things. Yeah.
To continue on this Brazil nut theme, so when you're driving your model, you're kind of inducing more shaking more quickly than you would naturally see, right? So you ran the model for about 100 days, right?
Right.
But do you have any estimate on what actual real-life timescales it would take to get that sort of sorting?
No.
Okay.
Short answer is no, but it's a good point. It's a fair point, making it more realistic, because these are, basically what I want to do is demonstrate this effect. They started this a long time ago, and it was kind of like driven by affect, literally, because I was like, hey, people keep doing this in cylinders. Why don't I'm using this code that can do this. So that's partly where it got started. And then what I want to do is do it as intensely as possible, and it'll show whether it happens or not. But yes, it needs to be more realistic in terms of impacts. And one idea is to actually take one of the marbles and smash it against it, right? So actually impact the object. And the reason I didn't do that is because it would get more complicated, right? As you add more objects to it. Already has 1,000 objects it has to track. Another question?
I have another question about that too. So you segregate out just to the 2 grain size, or not really grains, but in my head grain sizes, right? Yeah. Did you run any models with a larger distribution of grain sizes?
Not a distribution per se. One thing that I did do is look at this intruder model a little bit more, where there's one larger object. Sorry. So you can do an intruder model where there's only one large object, right, just like the cylinders, or 2 or 3, a few, basically. And you can shake it. And what I find is it only pops up to the surface if it starts off in the outer layers, which is basically what happened before as well. If that large object starts off in the interior, it just wiggles around and just stays in the inside. And these plots are showing the radial distance from the center of mass of the large object over time. And you can see it kind of, that's that cyan plot. You can see it starts off at that kind of transition point, and that's why it jumps out at the surface. But if it starts off in some interior point, it just wiggles around and doesn't go anywhere.
Any more questions?
Mark? Following up on this more, there's you made a bold statement that most asteroids are robopauls, and you made everybody in the room repeat that, even if they disagreed with it. But did you actually mean? I mean, how do you go from that very, very, very grossly simplified model to the sweeping statement that most asteroids are robopauls?
Right. I mean, we've talked about this. It could be like the degree of rubbleness could be different, where it could be a monolithic object that has a layer of rubble on the surface, right? So that it need not be completely rubble per se. It's just a lot easier to assume so for this. But yes, it's a fair point. It's not necessarily.
But do you think there might be a side where maybe your statement might be more true if you said something like most asteroids less than, I'm going to make the number up, 1,000 meters in diameter rubble piles?
So 150 meters and above, and I think, was it 10 kilometers? Maybe sort of. Yeah, there's a range, yes. Yeah.
Okay then, well, if there aren't any more questions, let's thank Varanga again. Now that all but let's excuse everybody but the committee members. And let's take like a 5-10 minute break. The committee will reconvene in here. Well, we'll probably do first one.
Okay, yeah, perfect. Take a break first.
Go ahead. We'll give it a couple.
Okay.